Championship with Team 4678 CyberCavs. I've got Rachel, Zach, Noah, Niam, and Sam with me here today, and they're going to walk me through the programming, their end effector, their awesome controller, and some other cool mechanisms on their robot. So what's the significance behind the red and white stripes on your chute there?
So this year's robot name is Orville. We named it because this big chute here, we thought it looked like a popcorn bucket. And so the chute, its main purpose is so that we can drive up to the feeder station, shove a coral down, and get it straight into the end effector as fast as we can. So you might notice that it's within bumpers. So at the start of a match, it is hooked on to the arm, but when we raise the arm up at the start of the match, it comes out. Can you just raise it up? So that way, with the gas shocks on it, we can ram right up against the coral station, and it will be able to absorb some of the blow, as well as allow us to have more time. Okay,
Are you able to collect a coral when there's a coral in front of you on the floor? If there's a coral between you and the station, can you still collect a coral?
Yeah, so even when there's a coral between the station, as long as we shove hard enough through the coral station, the coral should bridge the gap and make it into the bucket.
Awesome, thank you very much. So I haven't seen very many arms like this. Can you kind of go through the arm and the end effector?
Yeah, so this is called a cantilevered arm. It has an elevator at one side and an arm on the end. This allows us to go to any height really quickly. Intake. Go to L1. So we have an intake like, we hold our coral normally like this. Go to L1. So we can really quickly score on the lower level, the L1. Go to L2. And then L2, L3, and then even higher to L3, and then go to L4. Yeah. And so we can go from the resting position to L4 in half a second. Yeah. And so our end effector that holds the coral has actually gone through 8 different reiterations. Our first one that we put on the robot had 1/4-inch aluminum with a bunch of 3D printed parts on top, and it weighed a lot, but it had the same rough idea of 3 wheels with the flat side holding the coral.
Yeah, so is that the old one?
Yeah.
Awesome.
So after several iterations, we eventually got to one where it had an internal wheels to hold the robot. But the problem we found with this one was that the pivot point for the coral was way too far back. And an end effector like the one we currently have, we can put the coral anywhere on it. So when we're at L4, we can bring the bottom right to here. But when we need to do L1, we can bring it anywhere in between it. And this is also a lot lighter than our first iteration. We also have, this was our 4th iteration. It had 4 wheels, but the problem we had was that the coral would only get the edge of the wheels. And so it wouldn't hold it very well. It was very light, but it didn't hold the coral.
So with 3, you kind of get a good grip all the way around.
Yeah. This one, it's a little bit heavier, but it's lighter than the previous ones, and it holds coral really well. And it's not too hard to fix if bevel gear breaks.
Yeah, so are those 3D printed?
Yeah, so our bevel gears, we have a UHMW HUD on this is ABS, and the ones closest to the motor are actually nylon. So we started off making the entire bevel gear ABS, but what we found was that the HUDs on them would break too quickly.
I see.
So we eventually milled out a UHMW HUD, and it was much stronger, but we couldn't mill out a bevel gear on top of it. So we tried PETG with carbon fiber, and it's pretty strong, but it's too brittle. So as soon as there's torque, it shears the teeth off. What we ended up with the bevel gears beside the motor was nylon, which isn't as strong as PETG with carbon fiber, but it's a lot more resistant. And so when it takes the torque from the bevel gears, it doesn't shear off, it kind of moves a little bit.
Awesome, thank you very much. Okay, so you guys don't only do coral, right? How do you interact with the algae?
So yeah, we can do processor algae as well as knocking it off the reef. So for the higher algae on the reef, we can knock it off by swinging the arm up, or we can get the lower ones off by bringing this down, and that allows us to take it off the lower ones and throw it to the side. Or when we need cooperation points, we can also pull algae up off the floor onto the bumper. And these two bars on the side allows us to hold the algae.
And you can put it in the processor?
Yep.
Okay, so you've been controlling the elevator during this whole demo, and this controller does not look like anything I've ever seen before. So can you explain how this works?
So this is a custom 3D printed controller with a board inside of it. So this whole thing we made ourselves. We originally wanted the design to be able to be handheld, but later on we realized after putting it together that it's not as comfortable to hold as we thought. So right now I'm our operator, so I leave it sitting on the driver's station, and so this whole circle here of buttons signifies our reef. These two buttons here, this one goes to our rest position, and this one goes to our intake. All these 4 buttons up here go from L1, 2, and 3 all the way up to 4. Over here is our climber lock switch. So when we go to climb, I have to unlock it, and then I can press this to deploy our climber.
Very smart.
And so once the robot is disabled, the climber will actually lock itself automatically, so we don't have to do anything.
What are these yellow, orange, and green buttons on the side there?
So this one, as I said before, was for our climber to deploy it. This one is to pull our climber back in to climb. Currently, this one, and this one don't have any function right now, as well as the ones on the back. This one here we can use to force a position if our auto align doesn't work correctly.
So overrides?
Yeah.
Awesome. Well, thank you very much. Can you explain your climb sequence and the mechanism?
Yeah, for sure. So basically we have this mechanism here. So in here we've got some Dyneema cord, and then we've got our gas spring here, which will push out our climber, which also causes these elastics to open up our jaws so that we can grab onto the cage. Yeah, you want to open it? So yeah, and then also these feet will come out, and so these just grab onto the bottom of the cage. They rest on the bottom just to make sure that the claws don't slide and that it's always at a consistent place. And so we also have these polycarbonate sheets here that are a little bit slanted, so it can just guide the cage in, so it's not bouncing around and twirling and all that stuff. So it can just go in nicely like that, and just go right between the jaws. And then we have a Kraken motor in here that will spin a spool on the inside that pulls in the Dyneema cord. And then we also have a ratchet gear that is like this. You can see it right there, but this is a 3D printed version. And so when this is open, this is free to spin, which causes it to be able to go out and to come in.
And this is how you reset it at the end of the match?
Yeah, so this causes it to be able to hold once the power is cut. So there's an electric solenoid in there as well that will push the hull into the ratchet once the power is cut, so that our robot doesn't fall. So that will keep it up, and then just at the end of the match, someone will have to come and reset it, so then they loosen it. And yeah, so that's our climber.
Thank you. So can you explain how your automatic alignment to the reef works?
Yeah, so we have a LiDAR here, and that can tell how far away from the reef we are. And we can run a PID loop on that to bring us close to the reef. And then we also have a camera here that can tell us the yaw, the left and right angle from the reef. And we can use some basic trigonometry to calculate the left and right distance from the reef. But when we do that, it's important that we take into account the rotational error. Like if we're approaching at 130 degrees, but the target is at 120 degrees. So we account for that by adding the rotational error into the yaw angle. And then we can run a PID loop on the left and right distance to align the robot to the correct left and right distance from the robot. And We have each of these buttons that represents a branch. They just tell the robot which apron tag ID to look for, which side of the apron tag to approach on, and which rotation to turn to.
Thank you very much. Okay, and that has been an in-depth look at Orville at the Ontario District Championship. Best of luck for the rest of the competition, and thanks for watching.